Swayam Prabha. Digital India. Educated India.
Hello, everyone. Welcome to yet another session of our NPTEL on Nonlinear and Adaptive Control. I'm Shrikant Sukumar from Systems and Control, IIT Bombay. So we have this very nice motivating image in the background. This is of this nice SpaceX satellite which is orbiting the Earth, and we are, sort of moving towards designing algorithms which will help drive systems such as these autonomously. So we are well into the 6th week of this course and sort of at the halfway mark, if you may. And we have already started to look at design elements. So we have already started to see how to design adaptive controllers for a first order scalar system. And that's what we have been doing. So last time, we had already done the design in the session before last, and we had essentially arrived at a point where we had a negative semi-definite v dot for the unknown parameter case. So we had a control law, right? We had a control law we had designed, and we also had an update law for the parameter, for the unknown parameter. All right. So the control, of course, depended on this unknown parameter update. All right. So with this, when we analyze the system using this Lyapunov function that we constructed, in fact, the update law was obtained using the said Lyapunov function, and we got a negative semi-definite v dot. And what we did last time was to start from this point, this v dot, and use the signal chasing in Barbalat's lemma method of analysis, which we had learned sort of in the analysis part of the course in the first few weeks, right? And we use this v and v dot in order to prove that, we had already proved that we have uniform stability for the states, which are the error, that is the tracking error, and also for the parameter estimation error. All right. So what we wanted to do next was to prove that the tracking errors go to zero, converge to zero. So we already had a stability result. We wanted to sort of obtain a convergence result, right? Because stability is not enough, right? So that's what we did. We were able to prove, in fact, here, from step number 4, if you see, we were able to prove that the error goes to zero as t goes to infinity, right? So in spite of the fact that we don't know a parameter of the system, we were able to show that we can do accurate tracking just by adding a parameter update. And so this is the magic of adaptive control. This is what we did. Excellent. So I hope you sort of could see that there is this, rather cool element in adaptive control, right? And so now beyond that, we of course want to see if the other state, which is the parameter error, can also be driven to zero. All right. And we tried to do that, but honestly, we were not successful. Because we reached a point where we said that we found that the product of theta tilde in this function f goes to zero as t goes to infinity. All right. Now, if you sort of have something very simplistic, say, so this is where we start. I'm going to say lecture 6.4. I'm going to mark it here. All right. And you sort of so look at this, and then if you can make a very simplistic sort of assumption, which is probably not a very viable assumption, to be honest, I'll tell you why very soon. Right. So if we assume that f, let's see, limit as t goes to infinity, f x t t is equal to 0 is not equal to 0, okay, is not equal to 0, then there is hope. Okay, then there is hope that theta tilde doesn't actually goes to 0. Then can hope theta tilde goes to 0. All right, which is also not a guarantee. Yeah, I mean, so this is a rather complicated thing to talk about. Yeah, because we're talking about things converging to 0, and I mean, as t goes to infinity and things like that. So we are talking about objects in the limit. Yeah. Now, this itself may not be a very viable assumption in all scenarios. Yeah, it may be in the tracking scenario. Yeah. So, but notice that uh, your dynamics of the system was something like x dot is a f x. Sorry, I apologize. Was something like theta star f x t plus a control u. Okay. Now, if I assume that 0 is an equilibrium, then what you would have is that to ensure that 0 is equilibrium, typically you would have f0 t would be equal to 0 for all t. Okay, for all t, f0 t would typically be equal to 0. Okay, if that's not the case, then you can see that this right hand side being 0 and x equal to 0 and u equal to 0, and typically at the equilibrium the control is also expected to be 0. So the right hand side will not be 0 and it will not be an equilibrium. 0 will not be an equilibrium. So you would expect f0t to take on the value 0 for all time. Okay. Now if that is the case, here you see I apologize. Here I'm requiring f0t to be equal to 0, and here I'm requiring that as t goes to infinity, fxt t is not equal to 0. Sort of looks like opposite requirements. Now, if I'm looking at trajectories r, right, which actually go to 0 as t goes to infinity, this is possible, right? There's many possibilities. If I'm looking at say trajectories like this, it's like trajectory that is actually going to 0 as for large t. For large t, if you have the trajectory going to 0, then this is t and this is r of t. All right. Then this is difficult, right? I mean, this is a difficult situation where you sort of see that if r goes to 0, then as t goes to infinity, with the tracking error going to 0, x itself is also going to 0. So you can imagine that as t goes to infinity, this, by standard continuity type arguments, this function itself has to be rather close to 0. In fact, will go to 0 itself, right? So this is not satisfying. Yeah. So this condition is not going to be satisfied. Yeah. For all trajectories which are going to 0. Also for the stabilization problem where r of t is actually 0 for all time. Even in that case, this sort of a condition cannot be satisfied. So it's not very easy to have satisfaction of a condition of this kind. Yeah. So anyway, this is a naive requirement, I would say. Yeah, this is a naive requirement. So this is the sort of lesson in adaptive control. Yeah, and what is the lesson? Is that typically you can show that the state follows the desired trajectory accurately. This is guaranteed, no problem. Okay. However, parameter convergence or parameter estimation is never guaranteed. In fact, you need persistence of excitation for the parameters to converge to their true values. All right. So now, of course, in the previous week, we spent a lot of time before we go on to the second order system. In the previous week, we spent quite a bit of time looking at persistence and notions of persistence. All right. And so what I want to sort of do is try to give we almost don't in most circumstances analyze parameter convergence in adaptive control, and whatever we see in subsequent lectures. Yeah. Because parameter identification or any identification or system identification is a complete problem that predates adaptive control. Right? I mean, you can imagine if I want to identify, for example, parameters of a manipulator, robotic manipulator, you're expected to move the manipulator in all sorts of interesting or rich trajectory, if I may, yeah, so that you can identify the parameters of this manipulator. So you move it in all sorts of rich trajectories. All right, that's the idea. That's the idea. Now, this may not always be possible because we are talking about doing a control task. And we are not talking about just identification in itself. Okay, when you're doing a control task, you're expected to follow a certain trajectory, right? For example, a robot has to say move in a along a constant trajectory. Yeah, it has to say move along a straight line. Yeah, and not oscillate all around just to identify the parameters. That's not very okay as far as the operation of the system goes. And so it may not be possible to do good identification of parameters. So most engineers and adaptive control theorists are happy to have good tracking performance. Yeah, and if they do get parameter identification in the process, excellent. Okay. However, since we did do persistence and we studied persistence of excitation in the last week, let's just try to look at uh, what we can get out of this. Okay. So let's see what we have. Let's first write out the system equations, right? So what is E dot? Let's use this term. So E dot was minus KE plus theta tilde times fxt. Right? I think that was it. Right? This is it. Minus KE plus theta tilde fxt. This is what was E dot. And what was theta dot? Theta tilde dot? Theta tilde dot is just minus theta hat dot, which is this guy. Okay, so let's write it out. So theta tilde dot equals minus theta hat dot equals minus 1 over gamma times fxt times E. So if I write this in the nice matrix form, I get E theta tilde let's see if this is correct or not. Yeah, 1 over gamma E fxt, excellent, and this is right. Excellent, this is it. Okay, is equal to minus A. Then I have fxt. Then I have minus 1 over gamma fxt. And then I have a 0 here multiplying En theta tilde. Okay. Now, if you remember the lectures on persistence of excitation, you will remember that we had a very similar looking system when we were looking at this result. If you look at this result, yeah, you look at this particular system where we had these, of course, these nice requirements. AB is controllable, AC is observable. A had to be a Hurwitz matrix because then I can have this Lyapunov equation, and this phi function had some nice absolute continuity property. And of course, phi dot was L infinity. Then we could claim uniform global exponential stability for this entire system. Okay, great. So what does it mean? Sorry, okay, so went too far. Yeah, what does it mean here? So this system that we have here is very identical to what we got right now. This system. So let's try to compare. Okay. So first of all, what I'm going to do is, let's assume for the time being that f x t is f of t, and that it is independent of the state. Yeah, let's make our lives easy and assume that it is independent of the state. All right. All right. So that's one. So I'm going to nicely mark it because this is a big assumption, right? Because here we were talking about dependence with respect to x and all that stuff, right? But here, suppose I do make this assumption. Yeah. So then it starts to match this because it is exactly a function of time. All right. Now let's go back and try to write what these B, C, and A matrices are. So in this case, the A matrix is just equal to minus K, just a scalar. Right? The B matrix is just 1. The C matrix is 1 over gamma. So let me check if I got the signs right. Yeah, C matrix is 1 over gamma. Now let's see, is AB a controllable pair? A and B are both scalars, so trivially controllable. Yes. Again, AC are both scalars, trivially controllable, observable, no problem. Is A Hurwitz matrix? Yes, obviously, it's just a minus K. Minus K is a stable system. So that is to say that E dot equal to minus K times E is a stable system. It is in fact Hurwitz, no problem. And finally, if we assume further that this is F is absolutely continuous, yeah, and F dot is bounded, then the E theta tilde system is uniformly globally exponentially stable at the origin if and only if this f of t is persistently excited. Okay, and that's what it says here, right? So if I have all these conditions and we have this, we have proved A, we have shown AB is controllable, we have shown AC is observable, we already know A is Hurwitz because it's just a scalar minus K. If we assume that this phi, which is f of t in our case, is absolutely continuous and both the function and its derivative are bounded, then the system is UGS if and only if phi is persistently excited. Right? So that's exactly what you require. That f is persistently excited. So excellent. So with and what does persistent excitation mean? If you can recall the definition, for persistence of excitation, you don't need uh, the signal to be strictly positive at all times, right? So a signal can be persistent, yeah, even if it is going through zeros, even if it goes through zeros, like like signals like these, which pass through zeros, are still persistently excited. Okay, so that is the nice thing. Now, if you want to go back to the case where f in fact depends also on the state and not just a function of time, right? So I will just make a remark here, not actually try to prove it because it's a little bit more involved and complicated. So if f x t uh, if f also function of x, right? Then what do? You write f as, you still want to write it as a function of time, so you write it as a solution t at some t0 x0 and t. This is how you write fs. Okay, and in this case, if you go back again, we had this more novel result, or the more general result. It's the integral lemma result, right? And what did it say? What did it help us show? it helps us to show that for parameter varying systems also we can have similar results. Yeah, so we can have similar results for parameter varying systems also. This is just the parameter dependent output injection and so on and so forth. So it can be shown very easily using this integral lemma. We did not show it, but these results are available in standard literature, that this sort of a result that you have can be shown also when phi depends on some parameter lambda. And can also be shown when phi depends on some parameter lambda in addition to time. Okay, and then this is the result you need to use here. Yeah, so use lambda UPE plus integral lemma. Okay, now what's the deal with lambda UPE and integral lemma? See, notice that once I write this x here as the solution, which depends on time and the initial time and initial state. Let's, if you make our life simple and keep the initial time at 0, then this is a function of just the initial state parameter, or just one parameter. If you keep the time also, initial time also, then it's a function of these two parameters. Now you want a result which is independent of these parameters. Right? And how do we do that? By using lambda uniform PE, because that is what gives you uniform lambda uniform global exponential stability. That you get all the properties that are independent of the parameter. So basically, you start treating the initial conditions as parameters of the system, because they are. Right? I mean, once you fix an initial time and an initial state, it doesn't change for the entire duration of your run, your simulation, or your actual hardware experiment. Right? If I choose say 3 seconds when I start my robot, and I say that my robot starts in the XY plane at say point at the point 1, 2 in some Cartesian coordinate, then it's fixed for the entire duration of my hardware. Right? That is in fact a parameter. It is not. There's no time varying. There's no time dependence there. So we have reduced this problem to a problem of looking at parameter dependent systems, and this is where the integral lemma and lambda PE, we said that we introduced these more complicated notions, and we were sort of worried, or maybe some of you might have thought, why am I taking this excursion into more complicated things and what's the purpose and so on. But this is the purpose. I think most real scenarios you will have functions that depend not just on time but also on state. So what we do in those cases is we simply write the state as an evolution, right, as a solution, and then it depends only on these parameters, which is the initial data of the system, and then this initial data is the parameters, and we just want to uh, give properties which are independent of these parameters, or uniform with respect to these parameters. All right, so that's the idea. And so that's the idea. So in this case, you see that under conditions such as persistence of excitation and uniform persistence of excitation, or lambda uniform persistence of excitation, you can in fact prove things like uh, you know exponential stability. That is, you can get convergence of both uh, the tracking error and also the parameter error. Okay, great. Great. So usually it's not very evident here, but not if f is just a pure function of time, but if f is also a function of the state, just like we have here, and your state x is trying to track the trajectory r, it should be obvious to you that if the trajectory r is rich enough, okay, so this condition sort of reduces to, if you look at this lambda UPE sort of condition, this condition, yeah, this will sort of reduce to, um, you know, uh, R of t being sufficiently rich. Yeah, so reduce to R of t being sufficiently rich or containing sufficient number of frequency components. So when we do simulations and tests, that's what we do. Yeah, we want to see R with sufficiently large number of frequency components, which is what it makes the R of t signal rich. And if the R of t signal is rich, then the X solution is rich because it is eventually going to track the R signal. So lots of oscillatory signals, then you have oscillatory X solutions, and you have much higher chance of identifying the parameter. But like I said, already before, this is not guaranteed in real applications. In a lot of real applications, the trajectories you want to track are not super oscillatory with tons of frequencies and all that. You want to do nice, simple things. In fact, that's what you're designing controllers for. Yeah, you don't want them to do crazy oscillatory movements. Yeah, I mean, you don't want your robot to be doing this just to follow a straight line. So you want to do relatively simple things, and therefore adaptive control theorists do not care about parameter identification. Yeah, so if you want to do the system identification, it's a separate question. Yeah, um, if you have the freedom to do system identification, if your parameters are not going to change with time, then absolutely okay. You can do your system identification and then feed these parameters to a normal controller. Yeah, but if you do if you do not have the luxury of doing these kinds of experiments, for example, if you have 1-ton spacecraft which you cannot do so many oscillations of and do system identification experiments of, and there's a chance that these parameters may change in space conditions or high temperature conditions or very low temperature conditions, then you have no choice but to resort to adaptive control, where you don't necessarily get parameter identification, but you sort of are guaranteed to get precise tracking. Excellent. So good. Uh, so once we sort of understand what's happened in the scalar case and for the scalar system, we want to move on to using our wisdom, the same wisdom that we've already learned, to try to design adaptive controllers for the second order system. So we are just taking very like baby steps, one step at a time, right? So and please don't think that these are very trivial steps. Like most mechanical systems that you see around you can be written as second order systems. Yeah. But the thing is, here we assume that the system is scalar, that is, each state is in fact a scalar value. But for mechanical systems, these may be vector value, but that does not change too many things. Yeah, that does not change the fundamental ideas that go behind the adaptive control design. All right. So please don't worry about things being very trivial and very basic. It's very important that we get a handle on this first order and second order scalar systems very well, so that we understand how to do the design, what the issues are, and so on. So what is the setup? The setup is that you had this system, you had this right hand side already. We're just adding an integrator to it. You're just adding an integrator layer to it. Okay. So if you make a block diagram, I would make the original earlier system, and then I'll add an integrator. It's as simple as that. Yeah. So you have x1 dot is x2, and then x2 dot is given by this. Yeah. So the control appears here in the second layer. Control appears here in the second layer. Excellent. So, and as I said, the states are evolving in the real number space. The function is taking function f takes again the states and time and gives you some real numbers. Theta star is the constant unknown parameter, and u is as usual a scalar value. The standard second order scalar system. This is the setup. Right? What is the aim? The aim is now to design a control such that the first state, yeah, if you think of it as a mechanical system sort of notion, is the position. Right? You want the position state to track a smooth bounded trajectory. So we do not specify the second state, that is x2 state, because it is intrinsically related to x1 state by the derivative. Therefore, I cannot specify x2 arbitrarily. Right? Therefore, if I want x1 to follow r, x2 has to follow its derivative. Okay, x2 has to follow its derivative. There is no two ways about it. I cannot have instead of r and r dot, I cannot have r and 2 r dot. Yeah, I cannot have r dot by 2. I cannot have any variation. I cannot have r dot squared. I cannot have any arbitrary condition on the trajectory that x2 follows. Okay, so to make it simple, we refer to these such conditions as matching conditions. That is because these trajectories have to somehow be consistent with the dynamics of the system. So x2 desired has to equal the derivative of x1 desired. Okay, so the desired value of x1 has to, if you take the desired value of x1, you should get the desired value of x2. This is because it's dictated by the dynamics here. All right, great. So what did we look at today? So what we looked at today is we already had completed the analysis for trajectory tracking. We were successful. So of course we were very happy, but we could not prove anything about parameter convergence. So we sort of tried to leverage what we had learned in the last week to see under what conditions we can get parameter convergence. And so we saw that if you have only functions of time appearing in the dynamics, then you can use persistence of excitation. And if you have functions of both state and time, fxt, then you have to use parameter dependent, that is lambda u persistence excitation. Yeah. And then we sort of gave the setup for the second order scalar system that we are going to do adaptive control design for in the subsequent lectures. So this is where we stop today. Thank you for joining.